And as always, I'll do my best to post the recording to my YouTube channel. All right, so we finished off section 21.2. Now we're on to section 21.3. Aldol additions is where we're starting. So follow along with me in this section. There's going to be a little bit of curved arrows and some thought required here. So it says that when an aldehyde is treated with hydroxide or alkoxide, we get an equilibrium, right? If you treat this aldehyde, acetaldehyde, with sodium hydroxide, you actually have not only that aldehyde, acetaldehyde, but you also have the enolate in solution as well. I'm going to draw the form where we have the negative charge on the carbon. So we have both of these species in our reaction mixture, don't we? So if we have both the enolate and the aldehyde, the enolate can attack the aldehyde, and we get what's called an aldol addition reaction. So you can see what's going on here. The enolate is going to attack the aldehyde, and after you do a proton transfer, you're going to end up with this new compound that we call an aldol. Now you can see where the name comes from. It comes the ALD, right? The ALD comes from the aldehyde, and then we have an alcohol, so we have an aldol. So note that both of those functional groups are in here, and note the location of the hydroxyl, that it is on the beta carbon. So the hydroxyl is on the beta carbon in an aldol. All right, give me a thumbs up if you're with me on the rationale of that you have both the enolate and the aldehyde in solution. So we get a nucleophilic attack. Then after a proton transfer, we form the aldol. So we call this aldol addition when we form an aldol. Now, under basic conditions, again, we have the enolate and we have the uncharged form as well, the aldehyde. And so this is the mechanism that I drew. I just left out this first step here. I didn't draw the first proton transfer. What I drew was this on the previous slide. And then, of course, you have a proton transfer at the end to protonate the hydroxyl. Okay, and there you go. So this is a mechanism I expect you to know. Okay. I don't like to use the word straightforward in chemistry, but I'd say it's one that you should be able to put together: a proton transfer, nucleophilic attack, followed by another proton transfer. Now we are going to get into some details about this whole aldol addition thing here. So aldol, remember, we're forming an aldol in an aldol addition reaction. And it turns out that this is actually an equilibrium process, and that way if you have a simple aldehyde, and this is butyraldehyde, in that case, it says that the aldol is actually favored if you have a little old aldehyde like butyraldehyde. However, if you have a ketone, in that case, you're actually going to favor the ketone, and you're not going to end up with the aldol addition product. You can see that here it's only formed in about a 20% yield. So it's a very low yielding reaction, and low yielding reactions are kind of not very useful for us, are they? And if you're wondering, well, what's going on if I form the aldol? How do I go back to the ketone? And the answer is, if you remember, we talked about that any mechanism in the forward direction is going to be the same in the reverse direction, and we call that the retroaldol reaction. So once you form the aldol, it can go right back to the enolate and the ketone in this case. So it's just the reverse of the aldol addition. So do I expect you to know the mechanism of the retroaldol? I would say yes, because it's just the reverse of aldol formation. It's nothing more than that. Just one note that I've made to myself here in my notes is that this is the product of the enol or the aldol reaction. If you take acetone and you treat it with sodium hydroxide in water, you end up with this aldol product here. And the reason why you can lose this leaving group here and have a negative charge on a carbon is because it's resonance stabilized. So in case you are wondering, how do you lose a C minus again? Well, it's resonance stabilized, and so it's okay to lose that group. All right, so when an aldol product is heated, and this is going to be key, what happens to you and me when we get really warm? We tend to sweat and lose water, and organic compounds like to do the same thing. When you heat up the aldol product, you end up losing water, and you make an alpha beta unsaturated carbonyl. So you lose water, and you make an alpha beta unsaturated carbonyl. And we call that an aldol condensation product. Why? Because condensation, right? Loss of water. And you notice that the difference here is what? It's the heat. That is the key deciding factor. So if you just use sodium hydroxide and water, you're going to get the aldol addition product. But if you heat it up with sodium hydroxide and water, then you're going to get the aldol condensation product. Okay, so make sure you know the difference between the two. And you can see that they're shown here. The aldol addition, again, is going to be the reaction with sodium hydroxide and water, and that's going to give you the aldol. But if you treat this with sodium hydroxide in water and you heat it up, in that case, you're going to get the condensation product. And something that's interesting about these whole condensation versus addition products is that when we heat it up, it doesn't mean you heat it up sky high to 150 degrees or anything, 150 degrees or anything crazy like that. It's actually usually very mild heat that we need in order to make the alpha beta unsaturated aldehyde. And why is that? It's because the driving force of this reaction is the formation of a conjugated system. So we'll put here driving force, okay? So we'll put here conjugated system is the driving force of the reaction of the aldol condensation, right? Remember that conjugation imparts some stability to our molecule. Anyhow, there we go. So let's move on and let's take a look at the mechanism of aldol condensation. So we've already covered the mechanism of aldol addition. So there's nothing new in part one. This has all been covered before: proton transfer, nucleophilic attack, second proton transfer. So how do we eliminate the water? Well, in order to eliminate the water, we remove an alpha proton. So you can see that the hydroxide is removing an alpha proton. And then we end up losing a leaving group. This reaction here, we call this an E1CB reaction. So E1, so since you're doing an elimination and it's one at a time, we call this an E1CB, and the CB stands for conjugate base. I'm not going to go into detail on the E1CB reaction. The textbook mentions it a little bit, and I used to teach on it a little bit more in this class, but I've since realized that it never shows up on an ACS exam, and I've never seen it in any DAT or MCAT materials or anything like that. So I just kind of said, well, the chapter is heavy enough. But so if you want to look into the E1CB, go for it. Now you notice that the product that they drew here was the trans product, right? They just drew the trans product here. But we know that there are actually two alpha protons there, aren't there? There's this proton and this proton as well. And so you can actually get two stereoisomers. You can get the trans and the cis compound. And if you're wondering which one's going to be the major product, whichever one has less steric interactions, that's going to be the major product. End of story, okay? So just look at the compound. Whichever one has less steric hindrance, that will be considered to be your major product of your aldol condensation reaction. Now let's talk about these aldol condensations a little bit more. I'm going to show you some really cool nuances with these reactions. It says here that because the aldol condensation is favored, sometimes you can't even isolate the aldol, even if you wanted to. So if you were to take this compound, which you know the name of, right? This is acetophenone, and you treat that with sodium hydroxide, and you can see there's no heat here. You don't even get the aldol product. It goes straight to the aldol. Sorry, you don't get the aldol addition product. You go straight to the aldol condensation product, right? Why is that? Could anybody guess why you don't even isolate the aldol addition product? You go straight to the aldol condensation product in this example? Exactly. Thanks, Tiana. So we'll put here driving force. Driving force is formation of a fully conjugated system. Exactly. So you can't even isolate the aldol here, even if you tried to do it. Now, the yields for condensation reactions are usually much better than the yields of addition. You can see here that if we try cyclohexanone, we do an aldol addition. So again, this is aldol addition. We form the aldol product. But if we do an aldol condensation, we actually get a 90% yield versus a 20% yield. So a huge difference here. right? And again, the reason you get better yield is because you form a conjugated system. So better yield since this is a conjugated system. That's really the reason why we end up getting a better yield here. And when it comes to drawing the products of an aldol condensation, I'm just going to put a box around, you know what, I'll do it at the top, okay? Aldol condensation. If you want some practice on drawing the products of aldol condensations, it's covered in Skill Builder. It's Skill Builder 21.3. Gives you a really great method of drawing the products of an aldol condensation. And I'm going to practice that with you. I'm going to give you some tips on how to do that. So yeah, let's get to the next section here, which you might have been wondering about already, is what, so far, everything that I've shown you, every aldol addition, every aldol condensation, it's been the same ketone or aldehyde reacting with itself, right? Well, what if you have two different aldehydes and ketones? So here we have acetaldehyde and propionaldehyde. What happens when you put those in sodium hydroxide? Well, you can end up with the enolate of this guy, and you can end up with the enolate of this guy. So now you've got 4 different components in your reaction mixture, and you can end up with 4 different products, can't you? We call these crossed aldol reactions. So you see all the different aldol addition products that you can form here. So you can get, I'm not going to list them all, but you see that you end up with a total of 4 products. Are you with everybody with me on that? You can just get so many different products here, right? If you have 2 different aldehydes. Okay, so you're probably thinking, well, that doesn't seem very useful, forming that many products. It's not. This wouldn't be a very useful reaction for an organic chemist, having that many different products. And so there's ways that we can do crossed aldol reactions and actually control, or have some more control over the reaction, might be a good way to put that. So here we go. I'm going to show you how we can control a crossed aldol reaction to minimize the amount of products formed. So check it out. The only way a crossed aldol reaction can be practical is if we can minimize the number of products that we make. So there's a couple of ways to do it. Number one of the substrates is unhindered without any alpha protons. Well, you can see that formaldehyde, it's got a carbonyl here, but it has no alpha protons, right? Because there's no carbons attached here. So there's no alpha protons in formaldehyde, so you cannot form an enolate of it. Only the propionaldehyde can form an enolate, right? You could form an enolate of propionaldehyde, right? So if you form that enolate, well, then that can do a nucleophilic attack on here, and then you can form this aldol. Now, if you're wondering, well, why? How come this doesn't happen? I suppose it could happen, but the reason that this is going to happen preferentially is because formaldehyde is less sterically hindered. So that nucleophilic acyl substitution is going to happen first, okay? So that's one way to do it. And this is another example of the exact same thing. You can see that this is benzaldehyde here, and benzaldehyde has no alpha protons. So I can scribble that down here, no alpha protons in benzaldehyde. So if we make the enolate of propionaldehyde, right, it can do nucleophilic attack, right? After that, you do a proton transfer, and you can see that you can't even isolate the enol in this case, or sorry, the aldol addition product. The reason why is because if you do the aldol condensation, you end up with a fully conjugated product like that. So there you go. So those are some ways to limit the number of products that we get in an aldol condensation. Let's keep going about this crossed aldol thing here. Another way to do it is to do what's called a directed aldol addition. Now, this is something I've done a few times in my life, and I worked with a guy who was a real expert at these directed aldol additions. And I'm not going to draw the whole schematic out. I'll just kind of explain it to you. What you would do is you would take your ketone, let's say you had acetone here, and you would actually add the ketone to a flask with LDA in it. So you have a flask stirring, and it's got LDA in it, and you would take your ketone and you would add the ketone to the LDA. So as soon as the ketone hits the LDA is going to deprotonate it, and then you end up with a solution of the enolate, right? So you end up with a solution of this here, what is shown in red there. So you end up with a solution of the enolate, and then what happens is you're going to take this ketone and you're going to put it in here. this aldehyde, and you're going to drop it in here. So there's going to be a nucleophilic attack as soon as it hits that enolate. And so that's another way that we can minimize the number of products that we have, and we call that directed aldol addition. So you form an enolate in solution, and then you add this in. You add this in slowly, and every time it hits, it's going to react. Now, if you're wondering, well, why doesn't it deprotonate and react with itself? Well, the success of this reaction is going to be limited by the rate at which the enolate can deprotonate the electrophile. But usually we run the reaction at low temperature, and so the nucleophilic attack occurs faster than the deprotonation. Anyhow, so there you go. And then you could just treat it with an aqueous workup. I would actually cross this out. I would put H3O plus would be a better option here. Anyhow, and there you go. And you end up with your aldol addition product. Give me a thumbs up if that makes even like 60% or 65% sense to you. Okay, you're going to have to reread it, the directed aldol addition, but it is a very cool reaction. Now, if you're wondering, well, what if I have two ketones in the same compound? Can I do an intramolecular aldol reaction? Absolutely, you can, right? If you treat this compound with sodium hydroxide and you cook it up, right? Well, what are you going to do? You're going to end up forming an enolate, and then that can do a nucleophilic attack. You form the aldol addition product, then you lose water. You form the aldol condensation product. Now, if you're wondering, well, why wouldn't you form the enolate on the other side? Like, why wouldn't you form the enolate here? Why wouldn't you form the enolate here and do it like this? Because if you did that, you'd form a compound with a 1, 2, 3-membered ring. Remember, 3-membered rings are very unfavored in organic chemistry. So if you do the enolate the way they have it drawn here on the bottom left, then you have 1, 2, 3, 4, 5 atoms in your ring, right? 1, 2, 3, 4, 5. And you end up with the aldol condensation product. And there you go. It's a pretty cool reaction to make a cyclic compound. So with all that in mind, let's get a little bit of practice here on these. And this one, it says, predict a major product when each of the following aldehydes is treated with aqueous sodium hydroxide. Notice it says you treat this with aqueous sodium hydroxide, and it doesn't say anything about heat. Okay, so we'll put here no heat. Therefore, we're going to get the aldol addition product. Okay, we're not going to do an aldol condensation. So let's draw the enolate that would be formed. I'm just going to replace the aromatic ring with pH just so I have more room. So here is the enolate that we're going to form. I'm going to draw it with a negative charge on the carbon like this. And just since I don't have a lot of room here, what's going to happen is I'm going to do a nucleophilic attack on this. I'm going to form an alkoxide, and then I'm going to do a proton transfer. So after this step, I'll do a proton transfer. And what's my final product going to look like? So I'm going to start by drawing this compound again, but I'll draw it in blue. I'm going to try to color code this for you to make it a little simpler, okay? I don't know if that's going to work. Okay, I changed the color of my arrow. No, anyhow. Okay, so here's what we're going to do. We're going to redraw the aldehyde in blue like this, and I'm just going to move the chain, okay? Like this, okay? So there's the aldehyde in blue. Now, the one in black is going to be an alcohol now, right? So here's the first carbon. After the proton transfer, I'm going to have an alcohol. Then I have 1, 2 carbons, then my aromatic ring. So 1, 2 carbons, and then my aromatic ring. And there is the aldol addition product. Keep in mind, this is the alpha carbon. This is the beta carbon. The hydroxyl group should be on the beta carbon, right? This is an aldol. It's the aldol addition product. We're not drawing aldol condensation products. Let's try this again. If we take this compound, so this is cyclohexane carbaldehyde, we treat it with sodium hydroxide. I'll use color coding again. So we're going to form this enolate. It's only got 1 alpha proton. So we're going to form this enolate. And now it is going to act as a nucleophile. It's going to attack this compound. Okay. After the nucleophilic attack, we have a proton transfer. So I'm not going to draw the entire mechanism, but this is what we're going to have. We're going to have our 6-membered ring like this. We're going to have our carbonyl over here. Then we're going to have this carbon, which is going to have a hydroxyl attached to it. And it's also going to have a 6-membered ring like that. Okay, it's not the prettiest drawing in the world, but it's going to work. This is our alpha carbon. This is our beta carbon. So it's the product of aldol addition. Any questions about that? Or give me a thumbs up if you follow me on aldol addition. We're going to get to aldol condensation in just a jiff here. Alrighty, cool. Hopefully this is helpful. I find this is really fun to teach because it is a little bit challenging. So now what we're going to do is it says draw the condensation product when each of the following compounds is heated in the presence of aqueous sodium hydroxide. So look, I can go over this the long way and say, well, what we're going to do is we're going to treat this with sodium hydroxide and we're going to form the enolate. So let me draw the enolate, which is going to look something like this. Okay, here's my enolate. I forgot to do it in blue. Go. So now let's draw the enolate like this. It's going to do a nucleophilic attack. I can't see because I'm left-handed. There we go. All right, like that. And let's draw the aldol addition product. So after nucleophilic attack, proton transfer, I'm going to end up with something that looks like this. There's my 5-membered ring. There's my aldehyde. Then I have my beta carbon here. It's going to have a hydroxyl. There we go. And we'll put another 5-membered ring like this. And then, of course, this is going to lose water. So we'll put here minus H2O. All right. And then we're going to have a double bond formed here between the alpha and beta carbon. So when we draw the final product of this, it's going to look something like this. I'm just going to manipulate the rings a little bit here to make it a little bit tidier. So it's going to look something like this. So I'll draw the carbonyl maybe this way, and then put the double bond like that. Yeah, so then I just have this methylene and then the other 5-membered ring like that. So that's what you get after you lose water. Now, that's one way of doing it, but there is a simpler way of doing it. You want me to show you the way they teach you in the skill builder? So let me go over to a blank document and I'll teach you the skill builder method. All right, so here's the skill builder method. So this is skill builder 21.3, right? Skill builder 21.3. So what he recommends doing is this, is you draw the initial aldehyde like this, okay? And then what you do is you draw in the 2 alpha protons, okay? There they are. All right, everybody with me so far? Probably. Okay, so then I want you to redraw the compound, and I want you to draw it in such a way that you put the carbonyl facing, or the oxygen of the carbonyl pointing towards those alpha protons, okay? So let's draw a second molecule of it like this. There you go. Now what you're going to do is you're going to bring this compound next to this. So you're going to have the carbonyl oxygen pointing towards the 2 alpha protons. Now, when you treat this compound with sodium hydroxide, right, and you heat it up, you're going to get aldol condensation. So you're going to lose H2O. Well, what atoms do you see in red? The atoms here are H2O. So that's where your water, what happened there? This is where your water is going to come from. It's from these 3 atoms. So when you put those 2 molecules together, this is the product of your aldol condensation. It's going to look like this. You're going to draw a double bond here, and you're just going to attach it to everything that was over there, and you're done. And that's the product of aldol condensation. Give me a thumbs up if you follow me on that. Cha, anybody with me on that? Let's try the other one. So the other one was using 3-heptanone. So 1, 2, 3, 4, 5, 6, 7, like this. All right. Yeah, you like that one? Cool. Let's do it again, Audrey. So if we treat this with sodium hydroxide, right, and we heat it up, what's the final product going to look like? Okay, here's what we're going to do is we're going to copy this. Okay, so we'll copy it and I'll paste it. I'm not going to color code it the exact same way this time. what I'll do is I'll put these two protons in blue. I don't know what's going on with my Apple Pencil. I'll change the oxygen to blue. So again, you got these two things react, right? You're going to put these together, right, Audrey? And what you're going to do is you're going to lose H2O. That's it. You're going to lose water, so minus H2O, and then your final product is going to look like this. You have a double bond here, and then you're going to have 1, 2, 3 over here, and then 1, 2, 3 over there. And there you go. There's your aldol condensation product. Give me a thumbs up if you follow me on that one. What do you think of that? All right, so that's how you draw the products of an aldol condensation. Cool, cool, exactly. So now we're going to get into, looking at how would you make something when you're using two different aldehydes or ketones. So let's go back to the slides here. It's kind of a cool chapter, huh? We learned some really neat stuff in this chapter. Let me just, where were we? We were all the way down here. Okay, so we just finished 21.17. This one here, you're going to have to kind of bear with me on this one a little bit. It says, identify the reagents that you could use to produce each of the following compounds via an aldol reaction. And this one, it's just a matter of figuring out what are the ketones, what are the aldehydes? If it's an aldehyde and a ketone, what are they? And so here's my Sparks Notes version of it. You ready? There's a couple of things you can do, okay? If you have a carbonyl, and you actually always have a carbonyl, label the alpha and beta carbons, because in case you haven't noticed, this is where the bond is always made, okay? So you're breaking that bond when you're doing a retrosynthesis, okay? You're breaking that bond. And so the ketone that you would start with would be cyclohexanone, which is this. And then if you're wondering, like, how would I figure out what the aldehyde is? Well, you can see it's just going to come from this part here. So the aldehyde is going to be nothing more than this. We're going to make an aldehyde out of this guy that looks something like this. It's not the prettiest drawing in the world, but all we have to do is take those two compounds and mix them up with sodium hydroxide and water, and we're going to get the product. So this is the aldol addition product. Now, something that I've done historically, and I hate to post this to the internet because internet is kind of permanent, but something that I do which is not proper, but it just helps me sometimes, is drawing a backwards arrow that makes no sense whatsoever. So this was not created by any organic, this was created by yours truly. You can do kind of a backwards arrow like this, and then that'll kind of show you how the disconnection is done. But again, I can't really teach that because it's not proper. But if it helps you, you could try it that way. All right. So for the next one, we've looked at aldol condensations enough to know that this is where the bond comes from. And so retrosynthetically, what are we going to start with? We're going to have cyclopentanone, and then our aldehyde is just going to be benzaldehyde, isn't it? Right. So this in an aromatic ring like that. And what's our conditions? Well, it's condensation. So we need sodium hydroxide, water, and heat. Okay, and that's going to give us the aldol condensation product. Hot diggity darn. There you go. All righty. Everybody with me on those? Kinda? Yeah? All right. Let's try something where it asks us to draw a mechanism here. An intramolecular aldol reaction. It says draw a mechanism of the following reaction. Well, the first step is going to be deprotonation. I'm not going to draw the first step. I think you got me that you're going to remove an alpha proton and form this enolate. So then we're going to get a nucleophilic attack. Actually, you know what? Let me draw the enolate on the other side. It might make it easier. I'll draw the enolate over here. Okay. So first, what happened is, if you're lost on that, there we go. We have an alpha proton here. Then the hydroxide is going to rip off that alpha proton, and then you end up down here. Okay, good with me on that? All right, so let's get started on our mechanism here. We're going to do a nucleophilic attack like this. Now let's draw what we have. Now count the carbons very carefully. We've got 1, 2, 3, 4, 5. So let's draw our ring that we're going to form. It's going to look like this. 1, 2. So this is 1, 2, 3, 4, 5. And we make a ring there, right? There's a bond between carbon 5 and 1. So 1, 2, 3, 4, 5. And on carbon 5, we're going to have a methyl group. And then we're also going to have a hydroxyl group. Right? Or sorry, I guess it's going to be an alkoxide to start with. So we're going to have this like that. All right. So the next step is going to be a proton transfer, right? The hydroxide removed a proton in the first step, right? So you ended up forming the enolate plus water. So now we have water in the next step. So we have water behaving as an acid. And so our alkoxide is going to be able to pick up a proton there. And we're going to end up with the aldol addition product, which looks like this. All right. So now we need to do the E1CB reaction, right? So it's one at a time, and it's the conjugate base elimination reaction. So we're going to make the conjugate base of this compound. So we're going to remove this proton, and hydroxide is going to do it because it's our base. So hydroxide is going to pull off this proton, withdraw the conjugate base, which looks like this. And it's the conjugate base that's going to do the elimination, right? And you're going to lose hydroxide. So we're going to form double bond, and we're going to lose hydroxide like this. And there you have it. And that's in equilibrium, but there you go. That's the end. And of course, those last two steps, right? That's our E1CB mechanism right there. So there you go. There's our intramolecular aldol reaction. All right, it's getting pretty late here. Let me take a quick peek at Claisen. I think I'll just introduce the idea of Claisen with you, and then we'll call it a day. So let's look at the Claisen reaction. So I don't know if it's pronounced Claisen or Claisen. I guess, it's one of those. But anyhow, if you're wondering, could you do this kind of chemistry with an ester? The answer is absolutely you can, right? So esters also undergo reversible condensation reactions, and we call those a Claisen reaction or the Claisen reaction. So if you take an ester and you put that in sodium methoxide, not only are you going to have the ester, but you're also going to have this enolate. So I didn't really leave myself a lot of room, but you're going to end up with this. And then, of course, you can do a nucleophilic acyl substitution on that. I'm not going to draw the whole mechanism right this second. So you end up with what we call a beta keto ester. So you can see that we have an ester here. This is our alpha carbon. This is our beta carbon. And on the beta carbon, there's a ketone. So beta keto ester is what we get in a Claisen reaction. You heard this come out of my mouth just a few seconds ago. It's nothing more than a nucleophilic acyl substitution. That's all it is. The enolate is the nucleophile, and the ester is just the electrophile. So here's the mechanism. I think it's a very important mechanism for Chemistry 3111 students, and I've seen this show up on the ACS final. Okay, I've seen this in the ACS study guide many times. So the first step is we form our enolate, then we get our nucleophilic attack, and then we lose an alkoxide as our leaving group. Now, you look at this and you're like, well, that's the final product. Hold the phone. It's not the final product, is it? Because we know that this proton has a low pKa, and so the alkoxide is going to deprotonate it and form this doubly stabilized enolate. It turns out that the formation of the doubly stabilized enolate is one of the driving forces of the reaction, right? This, you could draw 3 resonance contributors to the hybrid. So what do we need to do? We need to protonate that. So in the second step, we treat it with aqueous acid. So step 1 is going to be our alkoxide, like sodium methoxide, for example. In step 2, we have to acidify using hydronium to protonate that doubly stabilized enolate. That's what we have to do. All right, well, let's move on from there and find out what the limitations are to the Claisen reaction. First of all, the starting ester has to have at least 2 alpha protons because the removal of the second proton, like I said, is the driving force to make that doubly stabilized enolate. Second thing is the hydroxide. You can't use that as the base because it will just hydrolyze the ester. It just does a saponification reaction. So this is just ester hydrolysis and base is saponification. So that's no good. That would destroy your starting material. And then another thing is that whatever your alkoxy group is, the base has to match it. So if you're doing a reaction with an ethyl group here, you would have to use ethoxide. Okay, you can't use methoxide because then that can act as a nucleophile and you get what we call that like, I forget the name, maybe I have it written in here. You want to know what I put in my notes? Mixture of products is all I wrote. But anyhow, you would end up with a mixture in that case, so that's kind of useful. Oh, the word is right here. It's transesterification. So you end up with both esters. You'd end up with the methyl ester and the ethyl ester in this case, and that would just make life miserable. So you can also do a crossed Claisen the same way you do a crossed aldol. It's just you have to follow the limitations. First of all, you want to do it where one ester has no alpha protons so that you can minimize the number of products. And you can also do a directed Claisen the same way you did a directed aldol, right? You treat it with LDA, and then you would add the electrophile into a flask containing this, and then it would keep reacting. And that way you minimize the number of products that you form. You can also do an intramolecular Claisen reaction. We call it the Dieckmann reaction or the Dieckmann cyclization is what it's called. I actually did a job interview one time, and I kind of walked in the office and started talking to these two people, worked at this company. And the first question they asked me was a Dieckmann reaction. I said, boy, I haven't thought about that in a long time. They said, that's why we asked you, Anyhow, so you can imagine that what you do here is you form your enolate, right? And then it's just going to do a nucleophilic acyl substitution here. And we're going to get some practice on this mechanism during the next class. So with also the last point says, like aldol reactions, Dieckmann cyclization, what's going to preferentially be formed? 5-membered rings or 6-membered rings, right? Those are the main rings that we want to form in organic chemistry. So with that in mind, let's see if we can draw the products of a Claisen reaction here. We'll just try one. So what's going to happen is we're going to treat this with ethoxide, right? That's what we want to use because we have an O-ethyl group here. So if we treat this with ethoxide, we're going to end up with some of the enolate, which is going to look like this. So we end up with the enolate, which looks like this. And then that can act as a nucleophile and a nucleophilic acyl substitution. So we form a tetrahedral intermediate. Then we lose the ethoxy as a leaving group. And so our final product after the loss of leaving group is going to look like this. So we're going to have our aromatic ring here. We've got this, okay, like that. And then we're going to have our carbonyl going in this direction. Oops. And then 1, 2, and our other aromatic ring like this, right? Because you're going to lose ethoxide in the reaction. All right, we'll leave this one for Friday. I'll give you a chance to try that one. And I think that I'll also give you a chance to try this one. Keep in mind that this is your alpha and beta carbon. Same thing here. This is your alpha and beta. So this is the bond you want to break. And you want to figure out what the starting esters would be for your Claisen condensation. And then here you want to do a Dieckmann reaction on either of these. So of course you're going to form an enolate like this, and that's going to react in a nucleophilic acyl substitution. And I won't draw the whole mechanism or anything, but I'll give you a chance to try that one before Friday as well. And then on Friday, the first new content that we'll look at is going to be alkylation at the alpha position as opposed to halogenation at the alpha position.